Welcome to our deep dive into mechanochemistry.
Oh, this should be fun.
It's all about how we can use mechanical energy to make chemical reactions happen, the kind you use every day.
Everyday energy for chemistry.
I'm really curious to learn more about this because I usually think of heat as the main ingredient to kick off those reactions.
You're right. We often associate heat with chemical reactions.
Yeah.
But what's fascinating about mechanochemistry is that it opens up this whole other dimension where mechanical force becomes the driving force.
Okay, so let's unpack this a bit.
Yeah.
What exactly do we mean by mechanical force in this context? Is it like, I don't know, stirring a pot really, really vigorously?
Well, stirring is a form of mechanical energy,
Okay.
but mechanochemistry takes it to a whole new level.
Okay.
Imagine, for example, a process called ball milling.
Okay.
Picture a container filled with metal balls. And the chemicals we want to react.
All right.
As this container rotates, the balls collide with the chemicals at high speeds, creating the mechanical energy needed to break and form chemical bonds.
So it's like a superpowered blender for molecules.
That's a great analogy.
Okay.
And one of the most amazing things about this is that these reactions can often happen without any solvents.
Wait, hold on.
Yeah.
I thought solvents were essential for most chemical reactions.
Yeah.
How can you skip that step?
That's one of the things that makes mechanochemistry so unique.
Okay.
By applying mechanical force directly to the reactants, you can overcome the need for a solvent. In many cases,
Wow.
the reactants are forced into such close proximity and with such energy that they interact and react directly.
That's pretty mind-blowing. And I'm guessing that has huge implications for sustainability, right? No solvents means less waste, less energy needed for heating and separation processes.
Absolutely. That's a major reason why mechanochemistry is gaining so much traction.
Makes sense.
Especially as we all try to reduce our environmental footprint.
Right.
It offers a cleaner, more efficient way to drive chemical reactions.
So we're talking about making chemistry greener and more sustainable.
Yeah.
But I've also read that mechanochemistry isn't just about making existing reactions more efficient. It can actually lead to entirely new chemical reactions and compounds.
That's right. By applying mechanical force, we can create conditions and reaction pathways that are simply not accessible through traditional solvent-based chemistry.
Oh, wow.
It's like opening up a whole new toolbox for chemists to create materials and molecules that were previously unimaginable.
Okay, now that is what I call pushing the boundaries of science.
It is exciting.
But I have to admit, I'm struggling to grasp how exactly mechanical force leads to these novel reactions.
Okay.
Can you help me visualize this?
Think of it this way. At the molecular level, everything is in constant motion.
Okay.
Molecules vibrate, rotate, and collide with each other. When you apply mechanical force, you're essentially adding a whole new level of energy and direction to those motions. This can force molecules to interact in ways they wouldn't normally, leading to unexpected rearrangements and the creation of new chemical bonds.
So it's like shaking up a box of puzzle pieces and suddenly finding that some of them have clicked together in new and unexpected ways.
Exactly, and those new combinations can lead to incredible discoveries.
Oh, cool.
From new pharmaceuticals to advanced materials with properties we never thought possible.
This is truly fascinating. I'm starting to see how mechanochemistry could revolutionize so many different industries.
It already is.
That's amazing.
And that revolution is already beginning.
Wow.
Scientists and companies are increasingly looking to mechanochemistry as a way to develop eco-friendlier processes and create a more sustainable future.
It's amazing to think that something as simple as applying mechanical force can have such a profound impact on the world of chemistry.
It really is.
But before we get too carried away with the possibilities, I think it would be helpful to take a closer look at the specific types of mechanical forces used in this field.
Yeah, let's do it.
All right, shear forces. Now, I vaguely remember this concept from physics class.
Right.
But I'm guessing most people are thinking shear what?
You're probably thinking of something like spreading butter on toast.
Okay.
That's a simple demonstration of shear force where you're applying force parallel to a surface, causing layers to slide past each other.
Okay, I can picture that.
Good.
But how does spreading butter relate to making new molecules?
It's all about scaling down the concept.
Okay.
Instead of a knife spreading butter, imagine incredibly tiny molecular-sized tools applying shear forces to molecules.
Right.
These tools can be designed to precisely control the direction and magnitude of the force, creating a highly localized, controlled environment for chemical reactions to take place.
So it's like molecular scale surgery using tiny tools to manipulate molecules with incredible precision.
That's an excellent analogy. And just like a skilled surgeon, chemists can use shear forces to carefully break and reassemble molecular bonds, creating entirely new molecules with targeted properties.
This is mind-blowing. It really challenges my understanding of how chemical reactions work.
It is a fascinating area.
It really is.
And the most exciting part is that it's not just limited to labs anymore.
Yeah.
The potential of mechanochemistry is starting to be recognized by industries looking for more sustainable and efficient ways to produce chemicals and materials.
I can definitely see why. But before we move on to those real-world applications, I want to make sure we fully grasp the key advantages of mechanochemistry.
Sure.
Would you mind summing those up for us?
Of course. In a nutshell, mechanochemistry offers reduced waste and environmental impact,
Right.
enhanced reaction efficiency,
Okay.
and the ability to create novel reaction pathways and molecules.
Yeah.
It's a powerful tool for driving chemical reactions in a cleaner, more efficient way.
Yeah.
And the best part is that this field is still relatively young, so we're only just beginning to scratch the surface of its potential.
That's a great point. It's exciting to think about what the future holds for this groundbreaking field of chemistry.
Me too.
Let's take a short break and we'll be back soon to continue our deep dive into the fascinating world of mechanochemistry.
Sounds good. Welcome back to our deep dive.
It's amazing to think about how much potential this field has for creating a more sustainable future. Before the break, you mentioned that mechanochemistry is starting to be used in a variety of industries.
Yeah.
I'm really eager to hear more about those real-world applications.
One area that's particularly exciting is the use of mechanochemistry in organic synthesis.
Okay.
This is essentially the heart of chemistry, where we build complex molecules from simpler building blocks.
So we're talking about things like pharmaceuticals, dyes, fragrances,
Right.
all those things that rely on intricate molecular structure.
Precisely.
Okay.
And traditionally, organic synthesis has relied heavily on solvents to dissolve their reactants and allow them to interact.
Right.
But as we've discussed, solvents can be a major source of waste and environmental concern.
Which is where mechanochemistry steps in,
Yeah,
offering a cleaner, more efficient alternative.
exactly.
Okay.
For example, researchers have successfully used ball milling to carry out a reaction called the Suzuki coupling.
Okay.
It's a fundamental tool in organic chemistry for building all sorts of complex molecules.
Okay, I have to admit, Suzuki coupling sounds a bit intimidating.
It's a mouthful.
Can you break that down for me? What exactly does this reaction do?
In simple terms, the Suzuki coupling links two carbon atoms together,
Okay.
forming a new carbon-carbon bond. This is crucial for building up the backbones of complex molecules, especially those used in pharmaceuticals and other important products.
So this reaction can be done using ball milling instead of solvents.
That's right.
That's incredible. Does that mean less waste is produced?
Exactly.
Awesome.
By grinding the reactants together with a catalyst and a ball mill, you can achieve the same outcome as the traditional solvent-based reaction, but with significant environmental benefits.
Okay.
You're essentially eliminating the need for harsh solvents and reducing the overall energy consumption of the process.
It's amazing how such a seemingly simple technique can have such a profound impact on the way we do chemistry. It seems like there's no end to the ways mechanochemistry can be applied.
And what's really fascinating is that it's not just about replicating existing reactions. Mechanochemistry can also unlock entirely new reaction pathways,
Okay.
leading to molecules that were previously inaccessible by traditional methods.
Now that's what I call pushing the boundaries of science. Do you have any examples of novel molecules that have been created through mechanochemistry?
One intriguing example is the synthesis of a special kind of polymer called a mechanophore.
A mechanophore. That sounds like something out of a science fiction movie.
It does, doesn't it?
Yeah.
But it's becoming a reality thanks to mechanochemistry.
Cool.
Imagine a material that can change color, emit light, or even release a drug when it's stretched or compressed. That's what a mechanophore can do.
Wow.
It's a molecule that's designed to respond to mechanical force.
Wow. So you could have a material that changes its properties in response to physical stress.
You got it.
What kind of applications would that have?
The possibilities are vast.
Oh, wow.
Imagine self-healing materials that can repair themselves when damaged.
Okay.
Smart textiles that change color in response to pressure, or even drug delivery systems that release medication precisely where and when it's needed. All triggered by mechanical force.
This is truly mind-blowing. I could see how mechanochemistry could revolutionize so many industries.
And that's just the beginning.
That's amazing.
As more researchers delve into this field, I have no doubt that we'll see even more remarkable discoveries and applications emerge in the years to come.
It sounds like we're really on the cusp of a new era in chemistry. But before we get too carried away with visions of the future, I think it would be helpful to ground ourselves in the practical realities of mechanochemistry.
Okay.
Are there any limitations or challenges that researchers are facing in this field?
That's a great question.
Yeah.
While mechanochemistry offers tremendous potential, it's not without its challenges. One of the key limitations is the difficulty in scaling up these processes for industrial applications.
I could see how that would be a problem.
Yeah.
So what's the hurdle in taking these fascinating lab-scale discoveries and translating them into large-scale production?
Well, bubble milling, for example, works wonderfully in a lab setting,
Uh-huh.
but it can be challenging to achieve the same level of precision and control when you're working with much larger quantities of materials.
That makes sense.
Yeah.
And I imagine controlling the temperature and uniformity of the reaction also becomes more difficult at a larger scale.
Precisely. Another challenge is the need for specialized equipment and expertise.
Okay.
While the concept of mechanochemistry is relatively simple,
Right.
the actual implementation requires sophisticated equipment,
Uh-huh.
like ball mills, ultrasonic grinders, or twin-screw extruders, and a deep understanding of the chemical and mechanical principles involved.
So there's definitely a learning curve for industries looking to adopt these methods.
There is.
What are those machines like?
We've talked about ball mills, which grind materials together using, you guessed it, balls.
Right.
Ultrasonic grinders, on the other hand, use high-frequency sound waves to create intense vibrations in a liquid medium.
Sound waves to do chemistry. That's wild.
It is. These sound waves cause cavitation bubbles to form and collapse. And when those bubbles collapse, they generate incredibly high localized temperatures and pressures.
It's like harnessing tiny explosions to drive chemical reactions.
That's a great way to think about it.
Wow.
Those extreme conditions can be used to break down particles, initiate reactions, or even create new materials.
Wow. So ball mills provide the force through impact and ultrasonic grinders through sound.
Yeah.
What about twin-screw extruders? You mentioned those before the break as well.
Twin-screw extruders are a bit more complex.
Okay.
They use two rotating screws to mix knead and heat materials under high pressure.
Hmm.
Think of it like a high-tech pasta maker,
Okay.
but instead of making noodles, it's creating new materials and driving chemical reactions.
So instead of impacting or vibrating the materials, twin-screw extruders are really putting the squeeze on them.
Exactly.
Okay.
And that squeezing action can be incredibly effective for certain types of reactions, especially those involving polymers.
It's fascinating how each of these pieces of equipment harnesses mechanical energy in a unique way to drive reactions and create new possibilities.
That's right.
Wow.
And it's not just about the equipment.
Uh-huh.
Researchers are also making significant strides in developing new catalysts specifically designed for mechanochemical reactions.
Okay, catalysts, those are substances that speed up chemical reactions without being consumed in the process.
You got it.
Okay.
And they play a crucial role in many chemical processes, including those driven by mechanical force.
Right?
But traditionally, catalysts used in mechanochemistry were often the same ones used in solvent-based reactions.
So what's changed? Are scientists now designing catalysts specifically for mechanochemistry?
Exactly. Researchers have started to design and synthesize catalysts that are optimized to work best under mechanical conditions.
That makes a lot of sense. So they're like tailor-made catalysts designed to be most effective when they're being well shaken and stirred.
That's a great way to put it.
Uh-huh.
These specialized catalysts can significantly enhance the efficiency and selectivity of mechanical reactions, leading to higher yields, less waste, and milder reaction conditions.
That's a big step forward. And I imagine it opens up even more possibilities for the types of reactions that could be done using mechanochemistry.
Yeah.
What other advancements are being made in this field?
Another exciting area is the use of computational modeling to understand and predict mechanical reactions. By simulating the behavior of molecules under mechanical stress, researchers can gain a deeper understanding of the reaction mechanisms and predict the outcomes of different approaches.
So it's like having a virtual laboratory where they can experiment with different conditions and forces without having to actually grind anything up.
Exactly. These simulations allow researchers to test potential reactants, catalysts, and reaction conditions in silico, saving time and resources in the laboratory and ultimately leading to the design of more efficient and selective processes.
It's like having a crystal ball that can predict the outcome of chemical reactions. That's incredible.
It's a powerful tool for sure.
Wow.
And as computational power continues to increase, these simulations are becoming even more sophisticated and accurate. This is leading to a much deeper understanding of mechanochemistry and paving the way for even more groundbreaking discoveries.
This really is the future of chemistry. But before we get lost in the world of computer simulations, I want to bring us back to the practical applications of mechanochemistry.
Okay.
You mentioned earlier how it's being used to create new materials.
Yeah.
Can you give us some specific examples of this?
Of course. One area where mechanochemistry is making a significant impact is in the development of advanced materials for energy storage,
Okay.
particularly in the creation of new electrode materials for batteries.
Okay, batteries?
Right.
Those are essential for everything from smartphones to electric cars these days.
Absolutely.
And the demand for high-performance batteries is only going to increase as we move towards more sustainable energy solutions.
Definitely.
How can mechanochemistry improve them?
Well, the mechanical force involved in a process like ball milling
Right.
can induce changes in the crystal structure and morphology of the electrode materials, leading to improved electrochemical performance.
Wow.
This means batteries that can store more energy charge faster and last longer.
So simply by grinding up the materials that make up a battery's electrodes, you can enhance their ability to store and release energy.
Precisely.
Wow, that's incredible.
And it's not just about improving existing materials.
Uh-huh.
Mechanochemistry can also be used to create entirely new materials with unique properties that weren't possible before.
Wow.
For example, researchers are using ball milling to create new types of polymers that are stronger, more doable, and even biodegradable.
This is really remarkable. It seems like mechanochemistry is playing a key role in the development of all sorts of clean energy technologies.
Absolutely. And as the world transitions towards more sustainable energy sources, the importance of mechanochemistry in this field is only going to grow.
It's inspiring to think about how this field of chemistry is contributing to a greener and more sustainable future. But before we wrap up this part of our discussion, I'd love to hear about any other interesting applications of mechanochemistry that you've come across.
One area that's particularly intriguing is the use of mechanochemistry in environmental remediation.
Okay.
Researchers are exploring the use of ball milling to break down pollutants and hazardous waste.
So they're basically using grinding to detoxify harmful substances. That sounds almost too good to be true.
It's a very promising area of research.
That's for
By applying mechanical force, we can break down complex molecules into simpler, less harmful substances,
Okay.
or even transform them into valuable products.
Can you give us a concrete example of this?
Sure. Researchers have successfully used ball milling to degrade pesticides, pharmaceuticals, and even plastics,
Wow.
converting them into less harmful compounds or even raw materials that can be reused.
Wow. It's like turning trash into treasure.
That's a great way to put it.
Wow.
And that's a perfect example of the power of mechanochemistry to address some of the most pressing environmental challenges we face today.
This has been such an eye-opening journey through the world of mechanochemistry. I feel like we've covered a lot of ground, from the basic principles to some truly mind-blowing applications.
We have.
But I'm sure there's still so much more to explore.
There certainly is. Mechanochemistry is a rapidly evolving field with new discoveries and applications emerging all the time.
Right?
It's truly a frontier of science with the potential to revolutionize the way we approach chemistry and manufacturing.
And as we become more aware of the need for sustainable and environmentally friendly practices, I think the importance of mechanochemistry will only continue to grow.
I completely agree. But for now, let's take a short break and we'll come back to wrap up our deep dive and explore some of the broader implications of this incredible field.
Welcome back to our deep dive into the world of mechanochemistry. We've covered a lot of ground, from the basics of ball milling to some truly mind-blowing applications in fields like medicine and environmental remediation.
It has been quite the journey.
And now I'm really curious to hear your thoughts on the future of this field.
The future is bright. What's truly exciting is that mechanochemistry is still a relatively young field. There's so much more to discover and so many potential applications yet to be explored.
It does feel like we're just scratching the surface of what's possible with this technology.
We are.
What are some of the areas you're most excited to see develop in the coming years?
One area I'm particularly interested in is the integration of mechanochemistry with other emerging fields like nanotechnology and biotechnology.
Oh, wow.
Imagine harnessing mechanical force to create nanoparticles with precisely controlled sizes and shapes. Or even using it to activate enzymes to catalyze very specific reactions.
That sounds like it could lead to some incredible breakthroughs.
Definitely.
I can already envision applications in drug delivery materials, science, and energy production.
Right.
It's like combining the power of chemistry with the precision of nanotechnology and the versatility of biology.
Exactly.
Wow.
It's a potent combination with the potential to revolutionize so many different industries.
Yeah, that's true.
Take self-healing materials, for example.
Okay.
This is something we touched on earlier.
Right.
Imagine a world where cracks in our roads seal themselves, scratches on our cars disappear, and even our clothes repair themselves.
I can't even imagine how much that would change things. It would be incredible.
It might sound like science fiction, but it's becoming increasingly plausible thanks to advances in mechanochemistry.
Wow.
And that's just one example.
That's amazing.
We're also seeing exciting developments in personalized medicine using mechanochemical approaches.
Personalized medicine is such a fascinating field.
It is.
It's all about tailoring medical treatments to an individual's unique genetic makeup and lifestyle. Right?
Yeah.
How does mechanochemistry fit into that?
Imagine designing drug delivery systems that release medication only when triggered by specific biological signals or mechanical stimuli within the body.
Hmm,
This could lead to highly targeted treatments with fewer side effects and improved efficacy.
that's a game changer. It's like having a drug delivery system that acts like a lock and key, only releasing the medication when the right key, either mechanical or biological, is present.
That's a great analogy. And as we learn more about the intricate workings of the human body, I believe we'll see even more sophisticated and personalized applications of mechanochemistry emerge in the field of medicine.
It's inspiring to think about the potential for improving human health through these kinds of innovations.
It is.
But beyond these specific applications, I'm curious to hear your thoughts on the broader implications of mechanochemistry.
Sure.
How do you think it will shape our world in the coming years?
I truly believe that mechanochemistry has the potential to fundamentally change the way we think about chemistry and manufacturing. It offers a more sustainable, efficient, and versatile approach to producing everything from medicines to materials to energy.
It's like we're entering a new paradigm where the old solvent-heavy methods of chemistry are giving way to a cleaner, more efficient approach.
Exactly. And this shift has the potential to create entirely new industries,
Wow.
lead to the development of products and technologies we can't even imagine yet,
Uh-huh.
and significantly reduce our environmental impact. It's truly a revolutionary field.
I completely agree. It's been fascinating to explore this topic with you. I feel like I've gained a whole new appreciation for the power of mechanochemistry and its potential to change the world.
I'm glad to hear that.
Thanks for joining us for this deep dive into the world of mechanochemistry. We hope you've enjoyed the journey as much as we have. Until next time, keep exploring the wonders of science.